Thank you for tuning in to the Grand Solar Minimum channel. Today I'd like to cover how a geomagnetic storm is ranked. A geomagnetic storm is a temporary disturbance of the Earth's magnetosphere associated with solar coronal mass ejections, coronal holes, or solar flares. A geomagnetic storm is caused by a solar wind shock wave, which typically strikes the Earth's magnetic field 24 to 36 hours after the event. Storms result in intense currents in the magnetosphere, changes in the radiation belts, and changes in the ionosphere, including heating the ionosphere and upper atmosphere region called the thermosphere. In space, a ring of westward current around the Earth produces magnetic disturbances on the ground. A measure of this current, the disturbance storm time, or DST index, has been used historically to characterize the size of a geomagnetic storm. In addition, there are currents produced in the magnetosphere that follow the magnetic field called field-aligned currents, and these connect to intense currents in the auroral ionosphere. These auroral currents, called the auroral electrojets, also produce large magnetic disturbances. Together, all these currents and the magnetic deviations they produce on the ground are used to generate a planetary geomagnetic disturbance index called KP. This index is the basis for one of the three NOAA space weather scales, the geomagnetic storm, or G scale, that is used to describe space weather that can disrupt systems on Earth. NOAA's 5-level system, the G scale, is used to indicate the severity of both observed and predicted geomagnetic activity. This scale is used to give quick indication of the severity of a geomagnetic storm. This scale ranges from G1 to G5, with G1 being the lowest level and G5 being the highest level. Conditions below storm level are labeled as G0, but this value is not commonly used. Every G level has a certain KP value associated with it. G1 is a minor storm. G2 is moderate. G3 is a strong storm. G4 is severe. And G5 is an extreme storm. With G5 storms, our power systems may experience widespread voltage control problems, and protective system problems can occur. Some grid systems may experience complete collapse or blackouts. Transformers may experience damage. Spacecraft operations may experience extensive surface charging, problems with orientation, and tracking satellites. High-frequency radio propagation may be impossible in many areas for 1 or 2 days. Satellite navigation may be degraded for days. Low-frequency radio navigation can be out for hours, and aurora has been seen as low as Florida and southern Texas. According to NOAA, this happens an average of 4 days per 11-year solar cycle. With a G4 storm, possible widespread voltage control problems and some protective systems may mistakenly trip out key assets from the grid. Spacecraft operations may experience surface charging and tracking problems. Corrections may be needed for orientation problems. High-frequency radio propagation may be sporadic. Satellite navigation degraded for hours. Low-frequency radio navigation disrupted. And aurora has been seen as low as Alabama and Northern California. According to NOAA, this happens an average of 60 days per 11-year solar cycle. A G3 is a strong storm. Voltage corrections may be required. False alarms triggered on some protection devices. Surface charging may occur on satellite components. Drag may increase on low Earth orbit satellites, and corrections may be needed for orientation problems. Intermittent satellite navigation and low-frequency radio navigation problems may occur. High-frequency radio may be intermittent, and aurora has been seen as low as Illinois and Oregon. According to NOAA, this happens an average of 130 days per 11-year solar cycle. With a G2 moderate storm, high-altitude power systems may experience voltage alarms, and long-duration storms may cause transformer damage. With spacecraft, corrective actions to orientation may be required by ground control. There may be possible changes in drag effect of orbit predictions. High-frequency radio propagation can fade at higher latitudes, and aurora has been seen as low as New York and Idaho. According to NOAA, this happens an average of 360 days per 11-year solar cycle. With a G1 storm, this is very minor. Weak power grid fluctuations may occur. Minor impact on satellite operations are possible. With G1 or higher storms, migratory animals are affected, and aurora is commonly visible at higher altitudes, including northern Michigan and Maine. According to NOAA, this happens an average of 900 days per 11-year solar cycle. We hope this has been helpful. Thanks for tuning in. Please like and share.